Yeah.
1 minute, yeah. You can chit chat for another minute, and then I will make ask people to turn off their video and audio, etc. I'll start the routine. Okay, it's 11:30 according to my watch, so I'm going to start the recording first. Okay, first request I want to make is please everyone except the speaker turn off your video and audio, and then when the Q&A session starts, you can turn back your video and audio. So let's get started. I want to start with the customary good morning, good afternoon, and good night for this around the globe audience that we have. This is our second IJMF Spotlight Seminar Series for the spring. We had a fantastic opening lecture by Professor Prosperity. This second act will be just as good, I promise you, because Rui is one of our top speakers. I want to remind you, as I stated 15 days back, that our objective is to promote particularly young authors who have had a influential paper recently in IJMF. We want to promote them, we want to publicize their work, and give them the spotlight, basically. So today we have Rui Ni, and he's going to talk about his recent work that he has published towards a model of bubble breakup in turbulence through experimental constraints. Rui joined the Department of Mechanical Engineering at Hopkins a few years back in 2018 as an assistant professor. And he got the distinction of being the Department of Energy ORISC professor. Before that, he was assistant professor at Penn State, and he received his PhD in the Department of Physics in the Chinese University at Hong Kong, and he was a postdoc at Yale after that. He has a number of awards or distinctions. He received the NSF Career Award recently, and he was also chosen ACS PRF New Investigator. And these are just the beginning. He is going to get many more awards. For example, being invited for IJMF Spotlight Seminar is an honor. He can hopefully add it to his CV or resume. So without further ado, I want to turn the floor over to Rui, and he's going to delight us with his bubble breakup models in turbulence. Rui, take it over.
All right, thank you, Bala, so much for your introduction. I want to do an audio check. Just want to make sure everybody can hear me.
We can hear you loud and clear.
All right, thank you so much. And first of all, I really want to thank everybody for joining today's IJMF Spotlight Seminar. I'm the second speaker. I'm on a lot of stress right now because the first speaker, Andrea, gave a very fantastic talk about his work, and I'm more of an experimentalist, so I'm gonna try to give a very different flavor of today's seminar on the experimental effort. Okay, I'm gonna continue here, and so I want to introduce the research in our group, and I focus primarily on the multi-phase flow. And general principle here is for multi-phase flow, we all know that typically, the two-phase flow is a sort of a simplest case. You have a carrier phase, and typically for the sort of a classical framework, canonical framework, we typically have a very weak turbulence, incompressible, and follow some kind of ambient conditions. And the dispersed phase is typically spherical, monodispersed, or homogeneous. But in a lot of applications, those kind of assumptions do not hold. For example, in ocean wave breaking process, air-sea transfer, you have this kind of very complicated air bubbles deforming and breaking in complicated intense turbulence. So in this case, we care about the deformable bubbles and droplets. I probably should change this to a pointer just to make it clearer. And We also have another situation where we could have a, okay, pointer doesn't really allow me to advance the slide for some reason. Okay, I'm gonna switch back to the cursor. Hopefully you guys can see it. And in this case, you have a complicated sort of a landing on the moon or Mars, where you're gonna, the exhaust plume of a rocket engine gonna actually generate a cloud of dust particles. In this case, the carrier phase is actually compressible. And we're also interested in particles that's non-spherical, because a lot of applications, for example, like biomass energy, we're talking about non-spherical particles simply because like the wood fibers actually are follow this kind of sort of a ellipsoidal shape. This is, even ellipsoidal is probably not the best characterization of the shape. So it's definitely non-spherical. We're also interested in multi-phase flow, where you have a complicated mass and sort of a heat transfer at an interface. Finally, recently we got an interesting project here on the active dispersed phase, active multi-phase flow, where you have a fish that actively modulates the surrounding turbulence. So the overarching theme in my lab is trying to pushing the frontier of multi-phase flow research to extreme conditions subjected to high-speed, strong turbulence, large mass loading. And today we focus primarily on the deformable bubbles and droplets and related to our recent publications. I want to just have a quick motivation here. We're trying to say that deformation and breakup are ubiquitous in many different applications, from wave breaking to chemical reactor to the oil disaster. So you always have this kind of important entities like bubbles or droplets breaking into smaller and smaller pieces driven by turbulence. And this is a very, very sophisticated problem. And a lot of people have contributed to this. And I think I really don't want to, I really want to acknowledge a lot of people's contribution, including a simulation effort from many different audience here today in the seminar. Appreciate your attendance. And I appreciate also comments about future collaboration we can pursue in this area. My focus today is actually on two different IJMF papers we published recently. One is back in 2019. This is more like a method we developed to reconstruct the 3D shape of deforming and breaking bubbles. I will start with this, and I will eventually jump into a recent publication. We're trying to use data we collected and to study the breakup dynamics in turbulence. And I want to acknowledge the students' contribution. Ashik Ashwansar, my former PhD student, they already graduated last year. Then right now they started their own career in Intel as engineers. And Inhe is a senior graduate student in my lab. He is basically lead author behind this work. All right. Before I get into the details of these two papers, I want to start by talking about the facility, because as an experimentalist, I really want to emphasize why we have a unique facility to study what we were interested in. And the facility we call it beyond said, this is simply a vertical water tunnel. And there's some special design features behind this vertical water tunnel I want to emphasize. So the first design feature is we have a mean flow, and the mean flow is adjusted to balance with the rise velocity of bubbles. And in this case, the mean flow, and at the bottom, we have this capillary island which generate bubbles, and the bubbles will rise up and encounter with the mean flow. So the flow, you can see that this is a case without turbulence, right? So you can see the bubble tried to rise in the mean flow, but they couldn't, simply because it's the mean flow sort of stalled the bubble rise motion. But the jiggle around simply due to this kind of a well-known the helical sort of a rise motion due to this bubbles. And the problem for mean flow is here is only 20 centimeters per second. It's not strong enough to create turbulence with a high energy dissipation rate that can actually deform and break bubbles. So in order to do that, we actually have to create a separate structure to generate the turbulence. And here, this is a test section, and this is an octagonal test section. I will tell you why in a minute. And on top of this, we have the jet array. So this is actually a special design 3D printed system. So there's some square holes here allow the mean flow to pass. On top of the square holes, you can see actually a lot of nozzles. We actually have 88 nozzles distributed uniformly over this cross section. And each nozzle is about 5 millimeters in diameter, and you can inject a very high-speed jet in coaxial with a mean flow into the test section. So this is basically internal structure of the 3D printed structures. And then we have the mean flow coming down, and we have jet going coaxially with the mean flow. And the jet can reach 5 to 15 meters per second. That can give you a very high energy dissipation in the system. And we can actually study, this is our view area, we can study complicated motion between the bubbles and the turbulence. And the basic bubbles are generated by the capillary island from below. Okay, And if I can advancing my slide. So in this system, we want to visualize the complicated dynamics between the two phases. And the one of the challenge we have experienced, I'm sure that many experimentalists in the office, they probably see the same problem. And I'm actually citing this work by Fujiwara back in 2000. This is a very nice view, a demonstration of the problem that the experimentalists encounter in multi-phase flow, in particular with large size bubbles. So typically, the standard technique we use, a so-called PIV system, is basically using a two-dimensional laser sheet to illuminate a particle and a bubble simultaneously. If you just use a classical PIV system, you're actually going to suffer from this kind of a very reflective interface. It's very hard to see the geometry of the bubble, and also it will also very hard to see tracer particle very close to it. So people start to use laser-induced fluorescence. Essentially, it's a technique using fluorescent particles to separate the spectrum emitted by the particle with a laser spectrum. Applying a filter, you can easily separate them. So you will remove the very shiny diffraction pattern here, but you will realize that there's a shadow created by this bubble simply because laser light coming from the right is actually being scattered away by the bubble. So you can't actually, the fluorescent particle cannot be activated by the laser. So that's why there are problems with this two methods here. And more recently, you know, Zaigenhan and Lucas did this work, also published in IJMF, is focusing on the shadow imaging. This is essentially using a light, LED panel from the back of the system, and basically this is a line of sight method. And they use the focal plane of the camera to just to focus on a sync plane near the bubble, so you can actually track the tracer particles around the bubble. Even though you can actually get a tracer particle very close, they still experience some challenges, including, you know, there's separate illumination requirement for two different phases for all three different methods. There's a concentration limit. If you want to track particles close to the bubble, there's a limitation of how high the concentration of tracers you can go. And actually, there's a problem of how close you can get the tracers near the bubble interface in order to resolve the interaction. So here you can see this is primarily 2D. In 3D, the tracer particle in the front or back of this bubble will actually be blocked by the shadow of the bubble, so you won't be able to see them. And finally, it's hard to get a three-dimensional deformation of bubbles in turbulence. And this one camera 2D method only provide one projection. So there are a lot of challenges with this problem. So when we approached it, we wanted to do a 3D measurements. And in order to do 3D measurements, so that's why we created this octagonal test section. And the octagonal test section essentially have 8 faces that we can actually have optical view. And then we position 6 high-speed cameras around the octagonal test section, so we can have a pretty good reconstruction of both faces. And so this is basically the sort of a picture of the experiment. You can see here it's illuminated by actually 6 LED panels on the opposing side of 6 high-speed cameras. And this is a top view here showing you this is the octagonal test section. And there's a big common area shared by all 6 cameras that you can really study the bubble in with the surrounding turbulence. And this is basically a raw video of a bubble interacting with turbulence. And you can see a lot of particles and close to the bubbles. And so we can use them to track the flow information around individual deforming bubbles. All right. So, and to do that, we typically get an image like this, and we separate the 2 faces. This is basically the bubble phase, and this is a tracer phase close to the bubble. And I'm going to zoom into this small region. I'm going to zoom. You can see that we have a lot of tracer particles here, and we paired our information, our data, raw data, with data collected by 3 other methods. You can see that we can get a lot of tracer particles close to the bubble interface. And the question here is, you know, this is really high concentration. Can we really track the concentration of tracers at this level in 3D? The answer is yes. And the trick is basically to use our open source Lagrangian particle tracking method. This is just one slide, but I have to tell you that this is 3 years of work from students Xiong Tan and also Ashwan Salabindra. And this is recently, we publicized this on the GitHub, and everybody can download it. And the really niche of this method is it can parallelize around on the HPC. You can really process a lot of the experimental data simultaneously. So this is really good. And also we designed this specifically for multi-phase flow. So this is a very nice package. I welcome everybody to use it. So with this tracer information, so we can actually identify that the flow in our system is pretty homogeneous isotropic. Here I'm showing you the U1, U2, U3, basically 3 velocity components. Solid line here show you the mean velocity, and the U prime here basically show you the fluctuation velocity. The axis, the horizontal axis here is basically the coordinates. Y is basically horizontal axis, Z is vertical axis. I want to draw your attention to those dashed line here. For perfectly homogeneous isotropic system, the 3 dashed lines should collapse with each other. In our system, they're pretty close to each other, but there's still a systematic higher vertical fluctuation simply because jet is primarily driving in vertical direction, which is also expected. But this is probably the best we can do in terms of reaching the homogeneous isotropic conditions. All right, so I want to take a quick break and just to slow down a little bit and summarize what we have talked about so far. So far we have been mentioned that the deformation and breakup are an important process in turbulence. And the V-onset is basically a new facility we created to study this problem. And in this facility features 88 individually controlled high-speed jets to drive the flow, and at the same time has a mean flow balanced with the bubble rise velocity, so we can reduce the bias of the statistics. And I also introduced that we can simultaneously visualize both spaces in 3D. We can get a lot of tracer particles close to the bubble interface. But there still remains a complicated problem here, which is can we really reconstruct the deformation of bubbles? This is very important because later on I'm going to tell you why the reconstructing bubble 3D deformation is crucial, because it affects a lot of statistics. So how do we do that? There is a standard way in the sort of a computer vision community. So this is a method that's called a visual Hall construction. And this method has been used by Alan Lawmire's group back in 2012, and they have a very nice way to illustrate the issues with the visual Hall reconstruction. So the issue here is that we always limited by the number of high-speed cameras we have, and typically you have 3 to 4 if you're working in sort of a single phase flow problem. So if you have 3 cameras, for any geometry you have in 3D, they're going to have 3 projections. And from these 3 projections, you can actually extrude it into the 3D space, and the intersection of this extruded volume will give you estimation of this geometry here. So you can think about basically all kinds of different geometries their group adopted before, from the sphere to all kinds of other shapes. And the sort of dark purple color here shows you the actual geometry, and this kind of a light purple here shows you the actual reconstructed volume. So the problem here is if you have like 2 to 3 cameras or 4 cameras even, you do this kind of reconstruction, you would get something. But the problem is there's always an overestimation of the volume respect to the actual volume. So there is a risk of doing experiments using a limited number of high-speed cameras. Okay, so that's the problem, and I'm going to demonstrate here again using our system. So here I'm just saying that there is a spherical particle here, and we have 4 cameras that start with a 4 camera because that's a sort of standard configuration for PIV or tomographic PIV 3D. So that's a sort of a standard way to deal with this problem. If you use 4 cameras in this configuration, on one side, you're going to have a geometry reconstructed look like a spindle. And the reason you have this kind of extra volume and sharp corners in this kind of configuration is because you don't have a camera which is perpendicular to the screen here to tell the difference between the virtual volume you reconstructed versus the actual volume. So how do we deal with this problem? So first of all, you could say, maybe I can just put another camera perpendicular to screen. There are 2 issues here. First of all, you may not have the budget to do that. Even you have the budget to do that, sometimes actually precluded by the experimental configuration. For example, in any water tunnel or wind tunnel situation, there will always be a direction that you don't have optical access simply due to the flow direction. So sometimes it's just limited. So in this case, if you cannot position the actual camera in that direction, what can we do? So we create a virtual camera method. So the virtual camera will be a camera that doesn't exist, but we position it at a direction that is perpendicular to most of the cameras, actual cameras. So this will be one of the virtual cameras. So basically, we position this virtual camera perpendicular to the screen right now. So the black line here showing you the projection of this reconstructed geometry for actual cameras. And then we can get this outline, and from the outline, we can find all the high curvature locations. And we know that for the bubble situation, there's a surface tension. Surface tension does not like high curvature. You always want to reduce the surface energy. So there's a physical constraint of the bubble geometry that does not favor those high curvature corners. So the virtual camera is essentially a way to enforce those physical constraints. So here I would say this high curvature should not exist. I'm going to smooth them. When I smooth them, I'm going to remove some materials from the reconstructed volume. But this removed material could potentially affect the projection in the actual camera. So in order to make sure I'm removing the material that doesn't really, it doesn't exist, so I have to check with the real cameras. So what I'm going to do is, whenever I remove some materials, I always check with real cameras, make sure the removed materials is basically not there. It's actually virtual material. So after iteratively remove this for one virtual camera, because the virtual camera is essentially for free, you can, so this is basically the final outline from this virtual camera. You can actually position many other virtual cameras, and they can always smooth the high curvature area from this kind of a black outline to this kind of red outline. After positioning many virtual cameras, you can actually get a much better reconstructed results. So in order to validate this method, we tried this with two actual camera with a spherical, and the gray area here show you the reconstruction without our method, and the bluish volume here show you the reconstruction with our method. So we actually reduce the uncertainty of the volume estimation by 30%. And here, if you use 3 cameras, and the original visual hall already does pretty well, a good job. But with our method, you still can reduce uncertainty significantly. Speaking of which, this is for 3 cameras typically used by most groups in multi-phase flow community trying to get 3 orthogonal view. You can see that even with 3 orthogonal view, you can still have materials that should not be there and still get into the reconstruction. But this is a simplified case. We also tried this with a dumbbell, because I believe dumbbell represent the case of bubbles when they experience breakup. And you can see that the reconstruction also does a pretty good job, also improve the visual hall, especially for small number of cameras. I forgot to mention that this is a 2, 3, 4, 5, 6 real cameras situation. When you increase the number of real cameras, of course, the reconstruction results are already close to the reality. But if you have a very small number of real cameras, our method can actually improve the reconstruction results significantly. And finally, we borrowed this direct numerical simulation data from Greta Tryggvason. So this is basically bubbles rising in, I forgot if it's channel flow or crescent medium here, but you can see there are a lot of bubbles, and we use 3, 4, 5, 6 real cameras, basically create a synthetic image to represent real cameras and implement our method to check if you can improve the reconstruction results. And the left figure here showing you the actual bubble cloud, and the right figure showing you the reconstructed results. And so with the visual hall, you can get roughly 20% uncertainty. With our method, you can reduce our uncertainty by half to about 10%. The details are included in the paper in IJMF. So finally, after validate the method, we're trying to make sure we can do this in experiments. So this is basically one bubble in experiments. I can tell you that this is just for the calibration case. So actually for real experiments, we have a lot more bubbles, and the 6 camera can really separate those bubbles reliably, even though some of them are overlapping one cameras. As long as there are other cameras capture them, you can still separate them. But here, in order to do the calibration, we only inject the bubble of known volume. So this way we can try to see if the reconstruction captures the actual bubble volume. So we use 6 cameras, and I'm going to show you, if you only use 2 real cameras, the horizontal axis here is actually number of cameras. You can also think about this as a dollar sign, if you may, because each camera costs quite a significant amount of resources to purchase. And the vertical axis is reconstructed volume. And the red line here showing the real cameras up to 6, then we switch to virtual cameras. So if you only use 2 cameras, you get something like a cube. This is basically without our corrections. And if you keep adding more cameras, you can get a refined geometry until you get 6. And after that, you can actually continue to remove the actual material by introducing virtual camera. I want to mention that the actual volume injected is about 62. So there's still a bit of gap between when you have to use a virtual camera, but this is a lot better than if you only use actual cameras compared with you only use actual cameras. So this is a very nice way to reconstruct a bubble geometry if folks have a limited number of high-speed cameras. So this is really give you a way to get a very nice results of bubble geometry. So this is published back in 2019. All right, so now I'm going back to the summary page. I mentioned that we have a facility that allows us to get a dense tracer particles. And up to this point, I hope I convinced you, we can also get a 3D deformable bubbles geometry reconstructed. And so right now, I can show you one very typical case. In this case, one bubble. I want to maybe pause here for a bit. This is the one bubble, and this is the 3D shape has already been reconstructed. You have many, many tracer particles around this bubble. We fix the volume just to see the evolution. Here we're showing a lot of trajectories of this tracer particle because we use Lagrangian particle tracking. We can really track all this dense tracer particle in 3D around the bubble. I want to point out this is actually only 2 millimeter size of bubble, and this volume here is about 6 to 7 millimeters. So this is actually very, very high concentration, if you imagine. And we have many and many of these cases reconstructed. Overall, we have about 10 to the power of 4 bubbles, and the tracer concentration is 100 times higher than that. So it's about 1 million tracer particles we can track simultaneously. So eventually you have a lot of statistics, so you can see breakup within the very complicated turbulent environment. All right. So what can be done with this data set? At this point, I'm going to go naively about some kind of simulation idea I'm thinking about. So this is actually, I want to mention that the simulation has advanced significantly in the phase flow community in the past 2 to 3 decades. I think Saeed Gobashi had a very nice annual review paper on this topic last year. And I think this is the experimental effort really need to catch up in order to provide more statistic and insight into this problem. But I want to provide a naive way of thinking about a simulation where you have a grid, when you have bubbles, but the bubbles are unresolved, so we had to model them. So in this case, if they're spherical, we already know pretty much everything about their behaviors. But what if they're deformable? So first of all, if they're deformable, you need to be able to predict the deformation based on the flow information here. So we published the paper using this data set that we actually measure the web number, local and instantaneous web number along individual bubbles. So in this case, you can really see the web number. This is instantaneous web number distribution, and we can actually connect them to the bubble aspect ratio, so that we can essentially get a bubble deformation. So in addition to the deformation, sometimes they have a different orientation. So we're also trying to use this data set to capture the orientation correlation with the surrounding turbulence. But when you get the orientation, you realize that orientation is going to affect the force experienced by bubbles. So we also did a paper on the lift and drag coefficient of the bubbles and their force correlation with the surrounding turbulence. And finally, the finite size bubble will modulate surrounding turbulence. They could have a wake. They could actually, when they do the deformation, they could absorb or release energy from the surrounding turbulence. And that's another paper we're working on, which is focusing on the deformation modulated turbulence. So this is basically what you can do with this data set. I really think we're preparing this 4D database. 4D means 3-dimensional in space and 1-dimensional in time. Everything here is time resolved. For deformable bubbles, that's what we are interested in. We're really trying to see how the deformation of bubbles in turbulence affect their dynamics. But today's focus is not only on those effects. I'm also interested in this breakup problem. So the breakup problem, you can imagine in the grid, you have certain bubble size distribution, and this bubble will actually break into a different size distribution when you vector it to a different grid at a second type. So this is my naive way of sort of thinking about simulation. So since you cannot really resolve all the bubbles, and the simplest model to use is this population balance equation. And the population balance equation is essentially saying, you have 2 terms that contribute to this kind of breakup process. The first term will be the gain. Essentially, a bubble of this size, D, here this is N is number density of a bubble of size capital D. And this the bubble of this size will gain number from larger bubbles. and through this kind of a term. And this term is basically integrate from this this bubble size to infinity, all the larger bubbles. And then we also subtract the loss term. And the loss term is basically based due to this bubble with this being broken into smaller sizes. So this is a very simple and very popular model that have been developed in chemical engineering community, but has been used in many multi-phase flow applications. I want to mention a few important parameters here. The first parameter is basically number of daughter bubbles, M. So a lot of the models have assumed that it's binary breakup, so M is basically equals to 2. And the other two models, the two parameters are very important. One is basically daughter bubble size distribution. Is essentially saying the probability of a mother bubble of size D, or size D naught, breaking into daughter bubble size of D, okay? And so this is a very important unknown parameter. And there's another parameter here, is breakup frequency. The breakup frequency can be associated with a particular bubble size. If it's associated with a mother bubble, it will be the GD naught. If it's associated with a daughter bubble, we call it GD. Okay, so that's the sort of just to define some parameters here. So here I want to show that we can measure the this bubble size distribution, right? Because we can resolve this breakup in 3D, so we can actually take some statistics. The first thing we did is basically we were trying to say how many bubbles actually break into this tube. So actually over almost 80% of bubbles breaking into undergoing this kind of a binary breakup. So the breakup that results in 3 or 4 or 5 daughter bubbles is actually extremely rare. And we also captured the daughter bubble size distribution here. And here I'm using a slightly different notation because I use the volume. And the volume here is range from 0 to 1. 0.5 basically means one mother bubble breaks into 2 identical sized daughter bubble. 0 means there's no 0, but very close to 0, that means the breakup resulting in one very small bubble versus one very large bubble. 1 basically means close to the mother bubble size. So as you can imagine, this is always symmetric because binary breakup always resulting in a smaller one and larger one, and the volume is always conserved. So that's why we use volume instead of bubble size. But you can easily convert this into the bubble size if you want. All right, so this is basically from our data. And we only have one data set, so we want to say, okay, what can we really use this to validate the model? And then we survey all the models, and we got a little bit frustrated simply because there's so many different models out there. And I want to apologize for the audience here because this is not a comprehensive list. We only picked a few models out of when I say few, I mean more like 10 models out of many different models. I think if the audience is interested in this, Leo and Lucas back in 2009 has a really nice review paper that summarizes a lot of effort before 2009. And since then, there's still a lot of effort trying to develop the new models. So the left picture here, you show the daughter bubble size distribution, and the right is basically the breakup frequency. And the only thing I can say is the model have a pretty large difference among themselves. But we don't have one data set, so we say, okay, maybe we can try to also survey all the experiments, or not all the experiments, and try to see if there's a common thread we can prove from experiments. So here I'm trying to show you 3 different experimental data from Hesketh back in 1991. This is in a PyFlow, and then Martinas Bazan's work in 1999. I think a lot of people are familiar with this work, and this is a bubble breakup in a jet. And then finally, this more recent work by Wajulaka. Their work is basically did it with a lot of jets and with a bubble. This is actually similar to our configuration. So within the 3 different experimental configuration here, they reported both the direct measurements of the daughter bubble size distribution and also the frequency. Okay, but that's not good enough for us because we want to see if we have other kind of experimental data set. Then we realized that there is a separate community in multi-phase flow. Is actually in the oceanography, like physical oceanography community. They're studying the breaking wave process, right? So actually a lot of work has been done in that community. So in the breaking wave process, they also have kind of bubble cascade or bubble breakup process. So in this case, they reported the so-called bubble size spectrum, which is essentially number density of bubble as function of size. And you can see that this number density information for both this breaking wave situation as well as for in the jet situation. So this is basically 3 different experimental results, 3 different types of experimental results that we can find in the community. So now the question is, how do we reconcile this experimental results? The first thing I want to show you is basically compile all the experimental results of this particular quantity, which is a dotted bubble size distribution, and compare with ours. So here I'm compile the existing. Again, this is not a comprehensive list. I apologize if you missed some important work. If you can send me an email, I would definitely include your data in the future for my presentation here. So this is a dotted bubble size distribution as a function of volume. And we include the pi flow, the jets, and 2 different jets experiment, and our case in the jet array situation. And I would say that this is the experimental results agree with each other pretty well, in contrast to the model, which are cover a fairly big range. So this is actually promising, which means at least the experimental data are consistent. I want to point out one thing here, is that although I spent most of our effort to do this in a homogeneous isotropic turbulence, because I believe that's basically what Hing's theory was intended for. However, this breakup model seems to work in a wide range of flow configuration, including the pi flow and jet that's subjected to the mean shear flow and other sort of effect in terms of breakup, but they still agree with each other fairly well. In this dotted bubble size distribution, I want to remind everybody the curve like close to 0 is actually represent this kind of uneven breakup, which is the breakup resulting in a small bubble that is much smaller than the mother bubble. And also there is a range close to 0.5. This is a basic symmetric breakup, which basically means that you have almost 2 identical dotted bubbles. And essentially the reason some models actually peak, for example, this kind of U-shaped model, the peak around this kind of uneven breakup, and some model like this bell-shaped curve by Martinez-Bazin, and that favors this kind of symmetric breakup, is because of physical mechanism that have been proposed to explain the bubble breakup. So this is essentially the underlying modeling strategy behind all this models. And previous works for the model essentially have this kind of 3-step. You typically have a physical mechanism argument. And the physical mechanism could argue based on the stress criteria and could also be based on the energy criteria. So essentially, this is actually fairly simple. It's just the turbulence stress minus the surface tension stress. And the problem, I don't have any problem with the stress condition. I have a problem with this proportionality, because every time you calculate this, you have to argue there's some kind of proportionality. And this proportionality could be the positively proportional or negatively proportional, or could be following the exponential function or parallel function. So it's very hard to know what is a right function to constrain this kind of proportionality. Same apply for the energy criteria. This is basically the surface energy of the after the breakup minus the before the breakup. So then Suris and Tavares, and back in 1994, they essentially argued there's a probability has to be inversely proportional to the energy. So that's why this model is sort of resulting in the 2 relatively symmetric breakup, and this result in sort of this uneven breakup. And so this is a more or less on the bell shape, then this is a U shape. And later on, there are a lot of more sophisticated models that include both criteria. So that's not really the focus of our presentation here. I'm just going to skip them. So here I'm trying to propose a new way to approach the problem. The new way here is very simple. I care about the physical mechanism, but I don't want to make any argument based on the physical mechanism. So instead, I'm trying to start from the experimental results and start from the data. And I'm trying to go backward and ask a question, which is, what is the minimum requirement of the dotted bubble size distribution that we need to have in order to satisfy all the experimental constraints? So this is basically the different strategy in terms of how to approach this breakup problem. Since I'm an experimentalist, that's only fair for me to start with data. One may argue that you already have a lot of data on the bubble size distribution, the dotted bubble size distribution, right? So if you have this data, why don't you just fit the data? Yes, you can do that. There's nothing wrong about it. My problem here is there is still uncertainty among different experimental data, also not as big as in the model, but there's still uncertainty, and I don't really know how to draw a line to connect this area. For example, it should be steep or should be a different kind of slope, or how do I do that? So in order to come up with a comprehensive way to include all the experiment data, we actually start from a different indirect measurements. Here, we're going back to this bubble size spectrum from different experiments here. So here, the only two experiments that reported bubble size spectrum, I think that's an incorrect statement. It's not only two, there are two out of many, and the two we picked is basically one is in the wave breaking, and this is the one in the jet situation. And the reason we picked these two because they actually are pretty following the same argument, because in the wave breaking case, the wave will entrain a large bubble, and that bubble will actually cascade or break into smaller and smaller sizes. And here in the jet situation, the bubble injected is largest, and that's slowly breaking into smaller and smaller pieces. So if you look at the bubble size spectrum, this is for the wave breaking situation. And in the community, in the wave breaking community, they reported two scaling laws. One is basically this minus 3 half. One is minus 10 power law. And in the this jet breaking situation, they have this kind of a spatially evolving size spectrum. If you overlay them against all together, you can actually see this kind of similar scaling law, which is minus 10. And this minus 10 scaling law is larger than this Higgs scale. And the Higgs scale, for those who probably not familiar with the Higgs scale, this is basically when the Webb number is close to the critical Webb number, let's say 4, and the bubble size is basically, at that time, is basically the Higgs scale. And the Higgs scale is separating the two regimes here. The regime on the right, we call it super Higgs. And in this case, this is basically a scaling that is fairly consistent, which is minus 10. And then for the scale below the Higgs scale, we call it Subking scaling. And I want to emphasize that essentially the classical model indicates that below the Higgs scale, the bubble have almost close to 0 probability of being broken, simply because the turbulence energy is not sufficient to overcome the surface tension. Okay, so that's why the critical Higgs scale is kind of important. And so this is the wave breaking community actually been chasing these two scaling laws for some time at this point, and this is a fairly consistent, at least the super Higgs scaling part being reported by many different wave breaking research. But how to explain this minus tensor? Actually, it's very, very simple. Garrett proposed a model. This is the equilibrium model. I can explain in 1 minute here, very easy. So you assume the bubble breaks into two identical sized daughter bubbles, so called size D, and continue to break into more daughter bubbles. Here, M here is the number of daughter bubbles. In this equilibrium model, M can be any number, and for simplicity, I call it 2. Okay, you can imagine because of volume conservation, the D will be cascading into daughter bubble size, which is M to the power 1/3 times D. And if assuming the breakup frequency is consistent with eddy frequency, so eddy frequency is a proportion to the size and also energy dissipation rate, you can write the breakup frequency for the mother bubble and daughter bubble. When the system reaches equilibrium, that means for any bubble size, the number of bubbles it gains and the number of bubbles it loses should be the same. So if you follow that argument, you can write down for this kind of daughter bubbles, it gains the number of bubbles equals to the number that being broken from the mother bubble. And this is a gain term, and the right side is basically the loss term due to the breakup of itself. If you write this equation and you simplify, consider the beam width, you realize that the number of bubble size distribution is actually follow this minus tensor power law. And here it's important to emphasize that this minus tensor power law does not depend on the daughter bubble size distribution. It only depends on the breakup frequency. If you don't believe me, we actually tried to numerically integrate the population balance equation using different daughter bubble size distribution. The way we did this is a population balance equation. We assume we know the breakup frequency based on the argument we had before. So G is sort of known already. We assume this is a binary breakup, so this is a 2. The only thing unknown here is F. So we can pick any model you want, so plug that into this equation, and then we only need to set up the initial condition. So for the wave breaking, the initial condition is basically I inject a bubble, a gigantic bubble at a particular size. And here I have a delta function at a larger size. And after integrate this equation over many, many steps, eventually cascade to this kind of broad spectrum of size distribution. And there is a one-to-one correspondence between the daughter bubble size distribution you picked versus this power number size spectrum you have. So one thing we realized that is this one, the super Higgs scaling, does not depend on any models we pick. Essentially, any model we pick, they always reach the same scaling law. It's just the time it reaches the scaling law is different. Okay, so this super hinge scaling is not useful to constrain a model. So this is basically doesn't work. But the super hinge scaling can help us to constrain the breakup frequency. So now we're looking at the subking scaling. The subking scaling, because I remind you that let me remind you that the small bubbles cannot be generated by within this range simply because this is below hinge scale, so bubble cannot be broken. So they actually had to be generated with a bubble that's much larger or larger than the hinge scale. So following this argument, you can see that you have to have this kind of uneven breakup in order to see the scaling laws. So this uneven breakup is related to the dotted bubble size distribution close to 0. If I have this kind of bubble size distribution, this is a U shape, you're gonna have a scaling law look like this here, which is a smaller slope compared with a -3/2. If I increase the slope of this dotted bubble size distribution close to 0, I can have a steeper slope here, which means in order to get the scaling of subking scaling for the experiments, I need to have somewhere in between. Okay, so there's a one-to-one relationship between the scaling law observed in the number density subking scaling to the actually dotted bubble behavior close to 0. So this is basically the first constraint we can establish. But what about the behaviors close to the symmetric breakup case? What about this range? As I mentioned to you before, this figure already used all the information. We use the super hinge scaling, we use subking scaling. So there's nothing else we can use to constrain the behavior here, close to the 0.5. So we use the Martinez-Bazens work. In this case, we can try two different cases, two extreme case. One is basically you almost have 0 contribution from symmetric breakup. In this case, you have majority of the cases uneven breakup. The other cases, the other limit is basically a lot of a contribution from the symmetric breakup. As you can imagine that when I have big bubbles introduced in the very beginning, so that it goes downstream, if we follow this kind of blue curve, what's going to happen here is bubble size spectrum probably doesn't change much. And the reason for that is because every time the bubble breaks, there's always one dotted bubble close to the mother bubble. Essentially, the bubble size doesn't change much as you cascade downstream. And for the other case, this is opposite limit where you have symmetric breakup. This is actually much more efficient. So in this way, the bubble actually reduce size fairly significantly over space and time. So we can actually implement this and compare with Martinez-Bazens report at a different window size. And here we choose the the blue one and the red one. And for the blue one, then we have 3 different experimental data at a different downstream location. X is basically downstream location. So the circle and this blue line is always matched with each other because this is the initial condition we picked. So we pick this initial condition, then we integrate the population balance equation. We get the 3 different, so two additional downstream locations. You can see that ideal case, the 3 lines should match with the 3 symbols, but in reality, they actually doesn't change much. And the reason the predicted curve doesn't change much is because exactly the point we mentioned before is that for this kind of uneven breakup, dotted bubble and mother bubble always the same size, so it's not very efficient. For the other limit, you can see that the same match at the initial condition, but the change of the bubble size spectrum is much, much faster and overshoot the experimental data, which means the actual data should be somewhere in between. All right, I think I'm running out of time here, so I'm going to summarize everything here. So we use a Subking scaling from Subking bubble spectrum scaling from the wave breaking situation to constrain the V close to 0, basically uneven breakup. And we use the jet breakup situation, the time evolution, to constrain the symmetric breakup. So eventually we have this kind of model, and the model function is basically written here. I don't want to emphasize too much on this model function here, simply because you can actually come up with a different function as long as you follow the scaling law here and you have a bump close to the symmetric breakup. And eventually we compare this with our own experiment data, compared with other direct measurements of this dotted bubble size distribution, which is a red curve. You can see that they all agree pretty well with each other. So the conclusion here is our proposed fit agreed with the 7 experiments in 4 different fluid configurations very well. And I don't want to say that we really settle down the debate here. And the reason for that is because we assume that this is a simplistic situation, right? But there could be complicated situations such as the bubble could be breaking into more than 2 pieces, and sometimes they could be dependent even on the local web number. So that's basically out of the scope of this particular framework. The final conclusion here is basically we constructed a nice facility to simultaneously measure the 2 different phases. We can use that really to provide a new insight into how deformable bubbles interact with the surrounding turbulence in a complicated environment. We also provide a nice way to sort of constrain the breakup model based on experimental data by using not only ours, but many other people's data. I want to really thank the committee and also the IJMF editorial board to give me this opportunity to share my research with everybody here today. And also I want to thank anonymous reviewers. I'm pretty sure some of them is probably in the audience today. I appreciate the suggestions and feedback. Thank you.
Thank you very much, Rui. That's a fantastic seminar. I want to take the opportunity to clap. The floor is now open for questions. I, of course, have some questions, but I'm going to hang in there and let others ask questions. Please unmute yourself and shoot your question.
I have a question. This is Rodney.
Go ahead, Rodney.
Okay, thank you. I'm very interested in these data size distributions and some recent study. There's a recent study that just came out in JFM by Luke Kadika's group at Princeton, and they argue that the data size distribution depends on the Weber number of the mother particle. What do you think about that? I think it's compatible with what you're saying, but I'm wondering if you're able to change the Weber number range large enough so that you could see the differences that they saw in they did direct numerical simulations.
Yeah, thank you. I think Lucas sort of sent me his paper before, so I think we're talking about the same paper here. I agree with you that as I mentioned, sort of as a last remark from the previous slide, that this is sort of the simplest model for the bubble breakup situation. And actually, Bojarska's experiment back in 2018 also suggests that this daughter bubble size distribution could depend on web number and also could depend on the number of daughter bubbles. But that's sort of a bit too complicated in the framework of many different applications. The reason I think they're too complicated is because as soon as the daughter bubble so right now the daughter bubble size distribution only depends on the mother bubble size, and sorry, that doesn't depend on anything. But if you start to link that to web number, to turbulence, to many other parameters, this becomes a very, very complicated multi-dimensional modeling problem, which is very, very hard to make it consistent from one test to the other. For example, not all the experiments reported the dependence on the web number or other parameters. So that's why we are aware of the complexity involved in this problem, but we didn't pursue that.
I guess my question is, can you do an experiment where you could change the Weber number over a range that you could actually look at look at a dependence on Weber number in the experiments like they did in the DNS simulations?
Yes, so the Web number we did is already covers 3 order of magnitude, because we are talking about instantaneous and the local Web numbers. And but over the 3 order of magnitude, 80% of that is still binary breakup. So, and so that's why it gave us a little bit of confidence about the data that there may be dependence of the bubble on the web number, but they're probably not significant in our experiments or in many other reported data. But Ronnie, I really don't want to say too conclusively. I really think this is an open question for the audience here to pursue in the future. Yeah.
I think just from I do modeling, right? So from a modeling standpoint, if you make the data size distribution depend on Weber number, that won't bother me, because I already know that the breakage rate depends on the Weber number. So it's just another parameter that I can put in. So it would be a 2 parameter. So I'm not too worried about that from computational if you can get me a function. So anyway, thanks for your answer. Very nice talk. I enjoyed it a lot.
Thank you, Ronnie.
Saeed, you had a question.
Yes, thank you. Well, excellent presentation. Thank you. My question is, how close can you get to the bubble surface to measure things like dissipation or kinetic energy or something that is required for modeling comparison with breakup and things like that?
I really want to say we can get really, really close, but the honest answer is we can get a rough. So, okay, I had to be clear. From a measurement perspective, occasionally you can have a tracer particle almost attached to the interface that you can get their location and velocity. But in reality, the statistic is not good enough. So in a lot of the situations, we had to increase the search area to about 2 diameter from the center in order to get enough statistic to talk about web number. So what we did is we correct the web number based on the inertial range scaling from a finite search radius to the exact bubble size. So that correction is inevitable simply because in order to include enough statistics, you had to go away. But I understand that this search radius is still too large if you want to capture the interface, the boundary layer close to the bubble interface. But it's good enough to capture things like wake. So in a lot of experiments, we start to see the wake effect simply because the wake sort of propagates a little bit further away from the interface. But in practice, it's about 2 diameter from the center. That's basically the search radius we had to use.
Oh, yeah, thank you. So what will be the obstacle for improving that situation in the future?
The obstacle is, the easy way to explain this is imagine my fist here is a finite size bubble. And if you have a camera in this direction, the bubble will block a number of particles here and here along the optical line. I'm not sure if you can see my fist or not.
Yeah, I can do. I see.
Yeah, so you need to have a camera from the opposing side in order to see this volume. But in order to see this volume, you actually have to have 4 cameras in order to get a 3D location, which means in theory, if you give me 20 high-speed cameras, maybe that's even on the estimation. Maybe you give me 50 high-speed cameras, I can give you almost DNS level data. But in reality, I'm limited by, even 6 is still too limited to get something exactly at the interface, if that makes sense.
Thank
and also,
you.
Saeed,
yes,
Saeed, I have one more point I want to make here is, I'm not sure having particle exactly at the interface is actually a good thing, because I had a lot of feedback from the reviewers that the bubble interface may be contaminated, and that so the interaction of tracer particle to the interface sometimes could cause more complication than benefit. So that's my last comment. Thank you.
Thank you, sir. Thank you.
We have a couple of questions on the chat. Charles Petty is asking, are the bubbles behaving as passive additives, i.e. They don't affect turbulence, or do they? That's the question. In your case, did the bubbles change significantly turbulence?
So that's a very good question, and that's why we're working on a paper trying to address that. So first of all, I forgot to mention that this bubble Reynolds number is fairly large, from a few hundred to a few thousand, depends on the size. And in the very beginning, when we studied their interaction with the surrounding turbulence, we are assuming they're only responding to the surrounding turbulence because the number concentration is fairly low. But later, when we look into that, we realize that the wake effect and also their active deformation will modulate surrounding turbulence. And we are trying to get statistics on that. It's just hard because if you have a lot of bubbles, you can get the mean turbulence modulation from the flow. But when you have like 10, 20 bubbles, you have to really focus on the wake behind individual bubble and have to rotate the frame, because wake is actually in 3-dimensional as well. So they're not always behind the bubble in the vertical direction. They're 3-dimensional. So we're looking into that, but just being a slow process simply because a lot of complexity in this problem.
Okay, thank you. That explains. So there's one more question which is going the other way. The question is, how much do the seeding particles, the particle that you seed the fluid, affect the surface tension in your experiments? And also, can you provide the size of your seeding particles? That's the question.
Yes, so our seeding particle is about 50 to 60 micrometer. We did not measure the surface tension, so I cannot really tell you how much surface tension has been modified due to the seeding particles. But we have one paper focusing on the rise velocity of the bubbles in intense turbulence. And using that information, we extracted the lift and drag coefficients in a turbulent environment. Then we compare the lift and drag coefficient against the previous models and the data on bubbles in purified and contaminated water. And we found out that the data of lift and drag coefficient actually closer to the contaminated situation, which indicates that the high concentration of tracer particles probably affect the interfacial dynamics, but but it's sort of in a consistent way compared with other sort of contamination people have done before. But that's inevitable because you either don't get background flow information or you contaminate it.
Anyone else have questions? Alfredo, go ahead.
Yes. Well, first of all, many thanks. The presentation was extremely clear, very nice, also very pedagogic. Many compliments on that. And I think you just said it that your tracers are about 50 microns, 50, right?
Yes.
So then my question is related perhaps to what Petty and Said already asked. So what type of turbulence indeed do you have around the bubble? Because bubbles do change through their surface tension, do change the topology, turbulence scales and everything. So if you come from an estimate of turbulence coming from, I don't know, some scaling, then what you actually do have in the proximity of the bubble interface is totally different thing.
That's actually a very good question. So I try to think about it because there are multiple things around I want to emphasize. So I want to first of all answer the first question. We have 50 micron particle size, and we also want to give you a rough idea of the turbulence scale. So the Kolmogorov scale is about 50, 60 microns. So the tracer particle is roughly the Kolmogorov scale. And the integral scale is about 1 centimeter to 2 centimeter. And so this is basically to roughly give you an idea of the inertial range we have. And the bubble size is about 2 to 4 millimeters. So it's in the middle of the inertial range we studied. So that's give you a rough idea of the scale we're talking about. Then you're absolutely correct that the bubbles are probably sometimes reacting to flow very close to the interface instead of the larger scale. But in reality, when we trying to find, so the bubble size, because it's in the inertial range, it acts as a filter to some degree. So it's not just the interfacial flow, because when we compare the bubble deformation against with the, for example, coarse-grained velocity gradient tensor, you can get the particles, you can capture the velocity gradient tensor at the bubble scale. And then you can compare the different eigenvectors. Say, let's say the most compressive eigenvector, which is trying to compress the bubble. And you can see a pretty good alignment between the compression and the bubble sine minor axis and the elongation with the bubble sine major axis. It provides some confidence that even though we don't capture the flow exactly close to the bubble interface, there's some kind of a large scale information that we can still capture and still be able to explain the bubble behaviors. And the third point I'm trying to make here is that there's energy associated with different scales. So because in turbulence, larger scale eddies typically have a larger energy, which means when you talk about bubble deformation, they're actually responding more close to the eddies of the bubble size. And small eddies contribution is still there. And they were trying to change the deformation into this kind of very weird geometry. So that's why in turbulence, you never really see ellipsoidal bubbles. You see these kind of funny geometries. And a lot of statistics we talk about today focus primarily on the large scale deformation at the ellipsoidal level. And the very fine, like local deformation was sort of ignored simply because we cannot, even though we can measure that from the bubble side, we cannot really get that from the fluid side. So I hope that answers your questions here. So,
yes, excellent answer, because also you are not looking for a very detailed model local for the microscale, but you're just looking for some model for one comment to the question of Blatzmakutz. He's asking how much particles change the surface tension, and it is our impression that not only do particles on a surface change the surface tension, but they do change it not uniformly, just locally, because particles tend to accumulate into specific regions. So you will have a very complicated interaction. So maybe you could estimate the amount of particles that end up sticking to the surface. But that was just a comment. And
that's actually So that's very insightful comment, and I want to mention that we actually thought about it, and I have a student that put a lot of tracer particles and have a bubble rising up and see the particle interacting with the interface and swept into the rear end and collected there. And we tried the same. We tried to search for the same thing in turbulence case, and we didn't find it. And my suspicion is that because the bubble reoriented so quickly, we actually have a pretty large energy dissipation rate. So the chromograph time scale is only 20, 30 milliseconds. So the particle may want to adhere to the interface, but it will be quickly spun back into the fluid. So it doesn't really result in a consistent accumulation. So therefore, we thought, even there may be some kind of a local accumulation may affect the surface tension and Maragoni flow. It's probably not important in this regime. For other regime, like in crescent rising, then that effect is probably non-negligible. So.
Okay, I have a question here again on the chat. Harry is asking, might be interesting, it disappeared. Let me put it up. Might be interesting to compare bubble breakup with those of drops. Apparently his students is performing Lattice-Boltzmann simulations and arriving at results that are comparable to what you are obtaining. So this is more a comment. And Rob Kunz, I don't know whether you want to add anything to Harry's comment.
I could just say one thing. I think the droplets, the reason I picked bubble in the very beginning is because I don't really know how to work with droplets, not because I don't know how to inject droplet into that water tunnel, but because the droplet there is a non-negligible viscosity effect in terms of the dissipation, the energy. So it's much more complicated than a bubble case, but we definitely want to collaborate with whoever has some data on this and to continue this effort. Thank you.
Thanks, Rui. Rob has a question. The iterative virtual camera algorithm seems to be a succession of smoothing operations based on curvature computed on 2D sections of the hull applied at different angles. Why not smooth the full 3D hull based on 3D curvatures computed from the previous iteration volume? Okay, so this was Rob's question.
First of all, very nice to see you, Rob, and thank you for attending my seminar today. So the reason, you're absolutely right. If we can get a reliable determination of the 3D curvature, we can simply do that. And the reason we end up with the virtual camera method is because it's impossible to get reliable 3D curvature from experimental data. And the reason, in simulation, so in simulation, you can imagine you have a very smooth interface. You can get a local curvature everywhere. But in experiments, your reconstructed volume is pixelated. So there are actually a bunch of blocks everywhere. So getting the three-dimensional curvature, you need to know exactly how to smooth that curvature. We started with that idea. We eventually abandoned it simply because it's not practical.
I have a question related to Rob's question. When you do these virtual cameras, you are essentially smoothing kinks that may appear otherwise. But what happens, but all the examples you showed are non-breaking droplets. During the process of breaking, then this process will break down, I suppose. So you have been mainly using pre and post breakup process, and during the breakup process, this virtual camera idea may or may not work. What's your thoughts on that?
Very, very nice comment. So first of all, we did a validation on the dumbbell. I don't think dumbbell is a best approximation of the breaking bubble, but it's one example of breaking bubble, right? So essentially the necking is probably what we're trying to focus on. So that sort of alleviates some concerns about the applicability of our method in that particular situation. But you're right. So there could be many the bubble could be breaking in many different manners, right? Different kind of weird geometries. The model still works, and the method still works. And the reason the method still works is because it's just a correction. So the breakup process still has to be captured by majority of the actual cameras, because if you don't capture that, you don't get a reliable reconstruction anyway. So the virtual camera will not be able to give you accurate reconstruction without a contribution from the actual cameras. So that's why we still require to have 6 cameras, because we want to have reliable reconstruction of the breaking up process. So sometimes you can get a better reconstruction because of angle breaking process. Sometimes you don't. That's sort of it's improvement. I don't want to make it sound like the virtual camera really can replace actual cameras. They can. They're just a correction.
Okay. I mean, this follows Rob's question. One way I sort of understand your algorithm is that given the 6 camera views, what is the smoothest bubble that is consistent with those measurements? Because it can't be smaller than those what you've seen in real cameras. But given those constraints, what is the smoothest possible? And that's what you have been able to get with these virtual cameras, adding them, and that provides a pathway for you to get the smoothest surface. Okay, maybe.
Thank you, Bob. I think you're putting this in a much better way than I did. Yes, absolutely correct. This is as smooth as possible based on the actual camera constraints. That's precisely the idea behind this.
Okay.
So Bala, I have a couple of questions from YouTube.
Please go ahead, Ted. Go ahead. You read them. Yeah.
Okay. Yeah. So from Sander Husman, I think this is also related to Rob's question. He says, for your bubble reconstruction using multiple cameras, do you also use the previous or next frames to decide what curvature is needed to describe the bubble the best, as volume should be conserved?
That's excellent. We try to implement that. The issue here is in order to enforce the volume conservation, sometimes we need to know where to add volume and where to subtract volume in each reconstruction, which is not practical. We thought about that. So we end up with using the volume conservation as a way to estimate the uncertainty. What I mean by that is, if you get a bubble volume as a function of time, because imperfect reconstruction, you're going to get this kind of oscillation in the volume. We're in the regime, the gas is incompressible. So in theory, the volume should not change. So we can use this kind of fluctuation of volume as a way to quantify the uncertainty, but unfortunately, we didn't get a chance to implement that in the reconstruction process.
Okay, and the second question from YouTube, from Ji Gao, in all the 4 experiments, is the bubble, does bubble breakup dominate while coalescence can be neglected?
Yes, so the concentration of bubble is so low, and the actual breakup process, so I try to remember, so the coalescence process is 25 times lower than the break process, and we exclude the coalescence process from the statistics, so we're sure they're not playing a role at least in the statistics we presented today.
Okay, thank you. That's all from YouTube.
All right, thank you.
Any questions from the Zoom audience? Well, if not, I want to report that we had about 100 plus Zoom attendees and about 50 YouTube watchers. So again, this experiment has been a grand success. I want to thank Rui for giving a fantastic talk, a good blend of physics, insight, experimental techniques, and pulling various people's data as well. So I want to give a round of applause and thank you very much.
Thank you so much, Bob, for
very much,
inviting
Rui.
me.